Hi, this is Mrs. Cribb, and we are going to go over the beginning of the Chapter 7 notes. Now, Chapter 7 will be some information that we're not going to test on unless you're in honors chemistry, but we do need to get familiar with it because it helps us understand polar bonds, and we do have to understand that according to the standards. So let's review really quickly about orbitals. Remember, the s orbitals can hold 2 electrons. There's one level, one sublevel, and it looks like a sphere. And the p orbitals can hold 6 electrons, and there are 3 levels or 3 shapes, and they're all dumbbell shapes, or they look like this on the x-axis, one on the y-axis, and then one on the z-axis that would go in and out. So there's the 3 shapes. The d orbitals can hold 10 electrons. There are 5 shapes, and I'm not going to draw them because they're too difficult. And the f orbitals can hold 14 electrons, and there are 7 shapes that we have. Remember, SPDF, we did this before, SPDF, 1, 3, 5, 7 shapes, 7 different orbitals, and each one can hold 2 electrons, so we multiply them all by 2 to get 2 in the S, 6 in the P, 10 in the D, and 14 in the F. SPDF 1, 3, 5, 7, and then 2, 6, 10, 14. Okay, we're going to need to review that a little bit because we're going to see that coming up. Now, covalent bonds, remember covalent is they're sharing, and they're sharing the valence electrons, involve 2 atoms sharing electron pairs with opposite spins. So remember, we saw some spin up and some spin down in the electron configuration. And we're going to review that here too. When 2 bonding orbitals are superimposed, one on top of the other, the overlapping space containing both electrons becomes available to both nuclei. That just means when they're overlapping, like here, you can see them overlapping in that middle area, this space is shared by both of the nuclei. Both atoms acquire another valence electron that fills the hole in that orbital, and this is called valence bond theory. Okay, now when we have valence bond theory and we're sharing, we have different ways of sharing. And so there are things called sigma bonds, and we're going to use this Greek letter, sigma. And a sigma bond can happen 3 ways. And a sigma bond, first off, is head-on. And we're going to do a little cheer when we get to class about sigma and pi bonds. But the sigma bonds, if I could draw it, I mean, I'm really, really horrible at it being an artist. Okay, here's a hand. 1, 2, 3, 4, and 5, okay? And here's another hand. 1, 2, 3, 4, and 5. And they come together straight on. Like, think about doing a fist bump with somebody. That's a sigma bond coming straight at each other, head on. Okay? Now, you can do head-on bonds 3 ways. You could have 2 s orbitals. There are 2 spheres collide in the middle. They're head-on. That's a sigma bond. You can have an s orbital and one of the p orbitals collide head-on, and so that area is still a sigma bond because they're head-on, they're coming straight at each other. Or you can have 2 p orbitals come straight at each other head-on and form a sigma bond. So sigma bonds can be formed by 2 s orbitals, an s and a p, or 2 p orbitals. And the p orbitals can only be hitting, only one part of the p orbital hits. They're straight at each other. So an ss overlap, an sp or pp overlap. Sigma bonds are the strongest type of covalent bond because the region of highest electron density probability lies on the bond axis. They always have these fancy words, but all it means is put these 2 guys together, and there's the axis. You could draw a straight line between the 2 atoms, and the electrons are right in the middle on that straight line in between those atoms. That's the bond axis. So here I can draw a straight line between these 2 atoms, and the electrons are right on that straight line, the bond axis, making it very strong bond, okay? Making it a very strong bond. So the sigma bonds are strongest because the electrons are on the bond axis, the straight line that's drawn right between the 2 nuclei of the atoms. So notice here we have an s and a p orbital, and when they overlap head-on, right here, that's forming a sigma bond. And now we have 2 of the p orbitals, And when they overlap, now this is a pi bond, that's wrong. This is a sigma bond. A sigma bond right here. Straight on. It's a sigma bond. This is still the best picture I could find for this. So y'all just need to make that small correction. All right. So sigma bonds are head on between two s orbitals, between an s and a p, or between two p orbitals. Okay, so right here we only had between s's and p's. This is an s orbital and this is a p orbital. But if I just had two hydrogen atoms, it would be two s's, because it'd be, the hydrogen and the s for the other hydrogen, and if they overlapped each other, that would be the sigma bond again. Those are supposed to be H's, they're just tiny. Okay, let's go on. Now, a double and triple bonds have to have something called pi bonds, and they form from the p orbitals overlapping. Now remember, here's the p orbital of one atom, and this would be the p orbital of another atom. And when they get, imagine these things getting closer and closer and closer to each other, just kind of scoot this thing over until it's right there, right on top of it. And they're overlapping at the bottom at the top. So that is one bond. This is overlapping at the top and at the bottom, but it's one p orbital overlapping another p orbital. That is one bond. It looks like two, but it's one, and it's a pi bond. And we use the symbol for pi like they have in mathematics. Okay? And so it kind of elongates. It's a pi bond, the top and the bottom. It looks like two bonds, but it's just one, because it's those balloons, here's one p orbital. So maybe that's the px and the px of another atom. And they get close together until they overlap on the top and the bottom, forming a pi bond. Now, I have a way of doing that in class as well. I'm going to draw my awful hand again. There's the first one. Here's the second one. And, we got elbows. I know that this is really horrible. Okay, so I treat this as the top of a p orbital. Like here's the top of one and the bottom of one of the p orbitals. And this is the top of a second p orbital on the bottom of another p orbital. And when they come close together, when the elbows and the hands touch, we form a pi bond. So a double bond would have a sigma and a pi. So sigma for so I'd say single sigma, double sigma pi. And so we'll do this little cheer together, and I'll make you all stand up. It'll be so much fun. All right, double bond between two carbon atoms. So what I'm showing you here is now we have a molecule, and this is the molecule we've actually drawn before, C2H2, when we had to figure out the Lewis dot structure. And so we did the whole available, needed, shared, and unshared. And the number available, carbon has 4, so there was 2 times 4, plus the hydrogen has 1 valence electron, because we're talking about valence electrons again. And so that's 1 times 2 for the hydrogen. So the number available was 8 plus 2. We needed 10, we have available 10 electrons. The number needed, every carbon needed 8, and there were 2 of carbons, and every hydrogen really needs 2 in its outer shell, and there's 2 of those. So that's 16 plus 4 is 20. We need 20 electrons. Shared was available minus needed. Needed minus available. And so needed is 20 minus 10, so we're sharing 10 electrons. And unshared is available minus shared, so that's 10 minus 10. None of them are unshared. Since they're all shared, we should have 10 electrons being shared. That's 5 lines. So, 1, 2, 3, 4, 5. Oh, that's what, look at that. I wrote 2 and there's H's. It's 4. So I got to go back and redo all that. Hold on, I'll pause it and fix that. Okay, fix that. C2H4. I was looking at C2. This is C2H2 down at the bottom. So this is C2H4. We're going to end up sharing 12 electrons, and every 2 is a single bond. So 12 divided by 2 is 1, 2, 3, 4, 5, 6 lines. So 1, 2, 3, 4, 5, 6. There we go. I'm happy now. 6 lines, and none of them were unshared. So we drew the Lewis dot structure, this down here, from this information up here. And this Lewis dot structure Well, it shows a double bond. This double bond is because we have one sigma bond right here in the middle. I'm going to make it black. One sigma bond head on between the pi. And then what happens is the p orbitals, this one, they're going to overlap each other, okay? They're going to overlap. They're right there. This is the pi bonds. On the top and the bottom, they're overlapping. And when they overlap, we get that second bond, that second pi bond. So here we have a pi bond, one pi bond, it's the purple, and one sigma bond, which is the orange. This one just didn't have it written in. That's why this was a little bit confusing. But they're meshing, they're really adding the p orbital with the sigma orbital here, the pi bond with the sigma bond here, to make the true picture showing you a double bond. This looks like a triple bond. Remember, p's overlap on the top and the bottom, so that's really only a double bond. Sigma in the middle, pi on the top and bottom. Now, the triple bonds have one sigma bond and two pi bonds. So single is a sigma, double sigma pi, triple sigma pi pi. Well, how does that happen? We have a sigma bond right in the middle, and we have a head-on between the p orbitals. We have a pi bond between this p orbital and the p orbital of the other atom. So these guys overlap. And then we have another pi bond between this p orbital and the back of the two atoms. They overlap. So we have two pi bonds. There's a pi bond on the red and a pi bond on the black. Okay, so when they show the overlapping, this big dark yellow is here. There's the pi bond, and the light yellow is underneath it, and it's really not super easy to see. So I think I found another one. Here we go. This is another picture of the same molecule. We have two carbon atoms, we have a triple bond, and we have two hydrogen atoms at the end. This is the C2H2, and this is the Lewis dot structure. And so here we have the blue p orbitals overlapping, the purple p orbitals overlapping, and then the sigma bond from the yellow p orbitals only touching on one end. So single bond sigma, double sigma pi, triple sigma pi pi. And we're going to practice that again in class. And then we're going to get to molecular resonance. So before we head into molecular resonance, I'm pulling up the Prezi for you to look at. Chapter 7 notes, this is just a picture of something called a tetrahedral, which we'll understand in a bit. And there's study sites at the beginning of it, some molecular shape simulators that we're going to use. There's your handy-dandy Quizlet to help you to go through the terms. I probably will assign the Quizlet for some homework assignments and perhaps give you a matching quiz on that information. And then all the different parts that we've already gone through. So we're going to pass through all this. But I wanted you just to see that all of what we've been covering is in the Prezi. So we will go through that again. And that brings us to molecular resonance. Now in the Prezi, one thing I like about it is it has some good pictures for molecular resonance. I'm going to draw it out for you, but I also want you to see it in the Prezi as well. Okay, so molecular resonance is when no single Lewis structure can completely describe the distribution of the electrons. There's more than one way to write the Lewis dot structure. We've actually already talked about that. Molecules act as if they are completely symmetrical with no experimental evidence, though, of a difference in the properties of the single and double bonds in molecules with molecular resonance. Basically, the bonds are all even in strength, and it's like there's an average between all the bonds. So you would not have a single bond and a double bond, but more like a 1.5 strength bond, an average. A molecule displaying molecular resonance. Now, I want you to, if that's the terminology, a molecule displaying molecular resonance does not oscillate. Oscillate, that means going back and forth. It does not go back and forth between two possible electron configurations. It's an average of them, an average of them. So let's look at the notes one more time. This is where we are. It does not oscillate. It's an average. Okay, so let's get the red. Does not oscillate. This is important because every year kids kind of get this messed up in their head. So I'm going to draw out the Lewis dot structure for this anion, because it's negative. So let's figure out our available electrons, valence electrons. Nitrogen, if you look on your periodic chart, nitrogen has 5 valence electrons and oxygen has 6. And this little negative symbol means we're going to add 1 extra electron. So we have 5 electrons plus 3, because there's 3 oxygen atoms, times 6, plus 1 more electron because of that negative charge. So that's going to be 18 plus 6. 18 plus 6 is 24 electrons. How many do we need? Every nitrogen really wants 8 in its valence shell. Every oxygen wants 8 in its valence shell. So that's 8 times 4, which is 32 needed. How many are shared? 32 minus 24. Remember, it's needed minus available. So that is 8 that are shared, and how many are not shared? Well, that's available minus shared, so 24 minus 8, so that's going to be 16. 16. Now, let's draw the shape. Now, this is where you've already done this, but there's going to be options. So nitrogen goes in the middle because it's missing more electrons than oxygen. Oxygen's missing 2, nitrogen's missing 3. Also, nitrogen's the oddball out. There are 3 oxygens, so you want to surround nitrogen with oxygen. So I'm going to put oxygen here, here, and here. I need to share 8, so that's 4 lines. 1, 2, 3, 4. And then I have 16 unshared. Well, nitrogen, see, it's got its octet. 2, 4, 6, 8. Every line is 2 electrons. But this oxygen only has 2, so we need to put 1, 2, 3, 4, 5, 6, because we have 16 to go. 2, 4, 6, 8, 10, 12. All right, now both of these oxygens have their 8. 2, 4, 6, 8, 2, 4, 6, 8. This oxygen, though, only has 2, 4, so it needs 4 more. So that should be 16. Let's double check and count them. 2, 4, 6, 8, 10, 12, 14, 16 electrons. So that is one of the possibilities. You have to put the brackets and a -1 sign, because the only way it has this configuration is because it gained that extra electron from someplace. It sucked it from somebody who didn't want one. Well, this double bond could have been on the oxygen, this other oxygen, or it could have been on this oxygen. So another way to draw this exact same ion is to put the double bond here and the oxygens there and the unbonded pairs distributed so everybody has their octet. That's one other way. But there's a third way, because that double bond could have been on any one of those 3 molecules, or 3 atoms rather. So nitrogen here with a double bond on the other side now. And we just put our Lewis dots, our alone pairs for our Lewis dots around the correct atoms. And there you go. This thing has 3 separate possible places to put the double bond. And they really are all identical, because imagine picking this guy up and flipping it sideways and you can make this. Or picking this guy up and flipping it sideways and make this. But there are 3 separate configurations. The thing is, in real life, you don't have a double bond here, and you don't have a single bond here and here. You really have an average. And that's displaying molecular resonance. When there's more than one way to write it, so that you end up with a double bond or a single bond in different places, you have molecular resonance. It does not change from this to this to this. It's an average of all 3. And that's what we call it when they have molecular resonance. So let me go back to the Prezi. Let's look at some of the pictures. Here's some other molecules that display molecular resonance. This molecule has a double bond between the 2 carbons over here, but a single there. But it could have been written with a double bond between these 2 carbons and a single there. So it really is both of these happening at the same time, an average of both. And it really looks like this, the average. And don't worry about the plus sign. We're not worrying about any of those kinds of things right now. We're just understanding that it has two possibilities. Here's another one. This is 1, 2, 3, 4, 5, 6. This is a benzene ring, and it has a double bond, single, double, single. And then another way you could have switched out those places. Well, it goes back and forth. No, it just averages out between these two. In fact, we write it differently in organic chemistry. But if I had to tell you to write something to prove it has molecular resonance, you would write both things. Here's ozone, O3. See that it has a double bond and a single bond, or a single bond and a double bond. It does not really go back and forth. It's really this average right here. And this says with a delocalized molecular orbital. We're not worrying about all these terms. We're just getting the idea that if there's more than one way to write it, in reality, it's an average of the two, and it's much more like this. But beyond that, it's pretty much beyond the scope of this course. This is a CO3 2-. Again, the double bond could be in 3 places, 3 possibilities. They should have put the brackets around these guys, but we're not going to worry about it. Is it 2-? Okay, might not be. All right, that brings us back to molecular orbital theory. So go back to your notes. Scroll down. Now, in molecular orbital theory, it suggests that orbitals of molecules, atoms are replaced by totally new orbitals. Okay, we spent all this time learning about the s orbitals and the p shapes and the d shapes where there are 5 of them, and f shapes where there are 7 of them. And, well, those are great, but when atoms are really working together, sometimes they kind of morph those things into something else. So each molecule has a unique set of orbitals equal in number to the sum of the atomic orbitals in the original atoms. So if I look at my Prezi, I have a picture that shows you that. Look at this. We have 1 s orbital right here, and 3 p orbitals right there. And so when we morph these guys together in this theory, we're going to take 1 of the s's and 3 of the p's, and that's 4 total orbitals to start with. 1 here, 1 plus 3 is 4, but we make 4 new orbitals that are all exactly the same. Before we had an s and 3 p's, but now we're making 4 new orbitals that all look exactly the same. And they're called sp3 orbitals because they're made out of 1 s and 3 of the p's. So 1 s and p, 3 of them, sp3 orbitals, and they look like this. Kind of like 4 exclamation points. And when you put them on top of each other, they make this shape called a tetrahedral. And we're going to go through that. We're going to make them in class and work through this very carefully. So don't get overwhelmed by this, okay? Let me escape out of here so I can do the next thing and find my escape button. Thanks. There it is. All right, so back to notes. Now, when we have this, we have something called bonding and antibonding. Bonding and antibonding orbitals. Because electrons behave like waves, remember they can be particles or waves. They can either help each other, reinforce each other, or interfere with each other, just like waves. So I have some pictures about that in a minute. Bonding orbitals are between the nuclei. They stabilize the molecule, and they have lower energy. Antibonding is an unfavorable way of putting things together. They're destructive, just like waves that interfere are destructive. And they're on the outside of the molecule and far from the nucleus. They have higher energy, and they spend very little time between it. Now look, here's a couple of pictures. Let's look at this one. Remember I said they act like waves? So this is called being in phase, right? And so the crests and the troughs are in phase, and if they hit each other, the crest becomes bigger and the trough becomes lower. This is reinforcing each other. This is bonding, what bonding orbitals do. But when an electron acts like a wave in a destructive way, where the crest and the troughs, the crest of one and the trough of another is in the same spot, they cancel each other out. Or when here's the trough and the crest of another, they still cancel each other out. So they get no energy. That's antibonding. This is not favored right here. And the other one is. So let's go back up and look. Here we go. antibonding and bonding. And bonding, first this is the original molecule A and molecule B, or atom A and atom B, and they come together, and if they're in phase like this, they reinforce each other, and the electrons form the bond in between the nuclei. And so this is where the negatives are, and these are where the positives are. And so positives and negatives are attracting, and so that's pulling each other together. Remember, likes attract. So if you put the negatives in the middle and the positives on the outside and negatives in the middle, well, they're going to be attracted to each other. And so that's going to pull them closer together to make this molecule. And when they're pulled closer together naturally, like the north and south of a magnet, so I'm going to draw that for a minute. Imagine this, okay? We have a north, and I'll put north on the other side, and south on the other side. When you put a north and south together, they're attracted to each other. They pull in tightly without you having to do much to it. It takes very little energy to get those guys to come together. But antibonding is the opposite. I'm going to draw another set of magnets, because antibonding is taking a north and a north, like on the north and north of a magnet, and a south, and trying to force them together. Well, here I'm going to actually have to push from the outside. I'm going to have to push these guys together, because there's this force in the middle, the magnetic force, that does not want to cross. So this is an unfavorable situation for a magnet. Same thing with these electrons. Electrons are negative and negative. In this case, they are moving to the outside. So the negatives are on the outside now. They move out here. And that means these two positive guys are in the middle. Well, positives and positives are likes, and likes repel. So the only way to force this together is to put a lot more energy. So notice the small amount of energy for these bonding orbitals, but it takes a large amount of energy to create the anti-bonding orbitals, because you're having to force it in. So that's the difference. Atom A and atom B prefer this, so it takes very little energy. They do not prefer this, the anti-bonding orbitals. They end up with nothing in the middle. The electrons are barely ever there, so we just have protons next to each other. And so that takes a lot more energy to make those atoms stay there. They do not want to stay there. They want to pull away. So that's the two types of things for this part up here, the molecular orbital theory, bonding and anti-bonding. All right, and that's going to bring us to molecular geometry. And we're going to spend a lot of time in molecular geometry next week, but we're going to work together with it, and it's going to be one of those things where it sounds a little bit harder than it is. So that's all I'm going to cover for this particular video, and so I'll see you soon.